Hello. So we studied how we can calculate confidence intervals for the y estimates uh, given a regression formula and given values of x, the um, experimental variable. And we saw two types of confidence interval. One, the confidence interval for the mean expected y value, and the second, the confidence interval, also called the prediction interval, for the distribution of all y values. So the prediction interval describes the area within which we expect 95% of, if we construct 95% intervals, then 95% of the y values should be lying within this range. And okay, that's about our confidence in the prediction, but we will also briefly discuss confidence in prediction outside the range of the observed x values, so outside the original data. So this is a pretty illuminating example from the book. So they've described how the age, how the length of the ear in humans changes with age. As you might know, cardiac tissue, it continues to grow. So people's noses and ears, they grow over time as they age. And if you plot the distribution of age versus the length of the ear, you see this positive correlation. And if we would construct a regression line based on this data, and if we would then use this to predict the age of a newborn baby, we would end up with something like, as you see, 55 millimeters. And ear of size 55 millimeters would look like this. This is, of course, a Photoshop. It's not a real photo, but it helps us see how absurdly large the ear of the baby would be. And this is an example of how extrapolation would not work in certain circumstances. Of course, it might work in some situations, but we wouldn't be able to know just with the data we have. We would have to rely on other types of information to judge whether extrapolation would be okay or not. If without external information, it would not be sound. It would not be correct to predict y values given x values which are outside the original observed data. Here you can imagine what's going on. The increase in ear length is obviously it appears linear within this range in adults, but it is most likely non-linear in early development, early postnatal development. So probably the curve looks like something like this. But yeah, we don't have any information about what's going on here. So it's most prudent not to make extrapolation, not to try to make predictions outside the original range. And yeah, prediction should be restricted to within X data limits. And now we continue with hypothesis testing. So we learned how to construct confidence limits on the mean of the predictions and also the predicted values themselves. But now we will be learning about how to calculate, how to test the hypothesis, the null hypothesis regression, which would be, as you might guess, that the slope is 0. That's the null hypothesis, and alternative hypothesis, slope not being 0. And we could test this. We can test this using a t distribution with degrees of freedom n-2. So this statistic, beta minus b minus beta, sorry, the observed calculated slope minus the hypothesized slope divided by the standard error of the slope, which we'll learn in a second. This is supposed to be t distributed with degrees of freedom n-2. In other words, again, just like we had touched upon also in the discussion about correlation, if the null hypothesis is true, if the real slope is indeed 0, then samples we would be collecting from such a population with mean slope 0, the real slope 0, samples we would be collecting from such a population would reveal a slope, an empirical slope that would, when we calculate this t statistic, they would be showing a t distribution with degrees of freedom n-2. Okay, if the null hypothesis is true, this statistic should be distributed with degrees of freedom with following a t with degrees of freedom n-2. And if the null hypothesis is not true, then this t statistic would be outside the t distribution. It's the probability of observing such a t statistic would be very low if the null hypothesis is not true. Okay, so we continue with another example from the book, and this is a study where they were checking how many, what kind of warning sounds a certain bird produces when it when it observes different types of predator, warning to warn its conspecifics against the danger. And the hypothesis was that the sounds contain information about the level of danger, such that if the predator is relatively small, there are more sounds, and if the predator is large, there are fewer sounds made. So the number of D notes that bird utters seems to be negatively correlated with the predator body mass. And we want to study whether this regression line, so based on this relationship, if the relationship is indeed non-random, if that is, if the slope is, if we can reject that the slope is 0 with this data, then we could use the regression function to predict the number of Ds per call given a certain predator body mass, right? A predator that is not in this list, we could predict how the bird would be responding to that call. Okay, and we want to first decide, of course, whether the regression, to be able to use the regression function, we first need to decide whether the regression function itself is reliable, whether the slope we calculate from the function is significantly non-zero or not. And for that, we need to calculate a p-value. And the 5 different statistics are already provided us ready. So from the data, what you might remember what we would need to calculate if we have such data. We need to calculate the mean. We, of course, first have to decide on which one is explanatory, which one is the response, and calculate the means of X and Y. and then calculate the sum of squares of x and y, each value minus the mean squared and summed up, and then calculate the sum of products. That is each observation in x minus its mean, each observation in y minus its mean, multiplied, and this performed for all the observations, 15 or something, and summed up. That's sum of products, sum of squares, the means. Good. And based on this, we can calculate the slope and the intercept. And we can also calculate the residual mean squares, right? So how do we calculate the slope? That was the sum of products divided by the sum of squares of x. And here we go. And how did we calculate the intercept? Well, we just plug in the slope and the means of x and y in the regression formula, and then we just solve for the intercept. And here we have our two coefficients, regression formula coefficients. And yeah, this is our, perhaps I can use the pen. This is our regression formula. And now we need, as a measure of how well the regression formula fits the data, we need a measure we need this measure called residual mean squares. As you remember, residual mean squares is the sum of squared residuals divided by degrees of freedom, and it's a measure, the smaller the residual mean squares, the better the fit. If all the data are on the regression line, residual mean squares will be 0, right? If all the data are on the line, then the predicted values and observed values are the same. The residuals are 0, so residual mean squares will be 0. The larger the residual mean squares means the worse the data fit the regression line. Okay, so we can use the residual mean squares as to estimate the standard, but not directly. We'll see that in a second. The residual mean squares is, as you might remember, you can estimate the predicted y values, that is y hat minus the observed y, or vice versa, it doesn't matter, squared. But there was also this shortcut formula here. You can use the y sum of squares and the sum of products times the slope divided by the degrees of freedom. And these components have already been we've already calculated, or we have already we've already been provided in the question, so we don't we can just use those components to calculate the residual mean squares. And yeah, we'd also seen that how to calculate an estimate of the standard error of the slope. B is the slope, right? That was residual mean squares divided by the sum of squares of x and the square root. So we can use those values. So we get B, A, residual mean squares, and if we divide that by the x sum of squares and take the square root, we have our standard error of the slope, and the t statistic would be the slope minus the hypothesized beta, but that's 0, right? The slope and the slope estimate divided by the standard error, and we get a t statistic of -3. So now, is that significant? We can calculate the p-value of observing such a t-statistic or more extreme or a more extreme t-statistic by chance using the t-distribution, or we can refer to the t-statistic critical values table at the back of the book, and there we can figure out that the p-value, the probability of observing this in a two-sided test is between 0.01 and 0.02. So it doesn't seem super likely. We can say there might be a real effect and the slope might be significant, and thus the regression function could be reliable and usable. Right, and this is how we perform hypothesis testing in regression. We will also briefly learn a similar approach, basically, but using an ANOVA table. So in ANOVA, as you remember, we had the group effect and the residual or error term. So the group effect was the differences between the mean or among the means of groups, and error or residual was the variance. It was an estimate of the variance within groups. And here, instead of groups and variance within groups, we have the we again divide the variance, the total variance. We divide it into two components. We divided the total variance is the total sum of squares, or I should say, is this the difference between each value and the mean. We divide this into the part which can be explained by the regression function, the predicted y values and the observed value squared. So this is the part that can be explained by the regression formula. In ANOVA, this was the difference between group means. Actually, it's pretty analogous. And this is the part which it cannot, this is the part of the sum of squares which can't be explained by the regression line. Okay, it's the leftover sum of squares. And the degrees of freedom of these two components are 1 and n minus 2. And we can thus calculate the mean squares, and the F ratio is the MS residual, what we had already calculated, and the MS of regression is just this difference. And we can run an F test on the regression for the regression formula for any data set as well. Here again, the logic we are using is very analogous to what we had previously studied. We're decomposing or separating the total variance into the fit part described by the regression formula and error. And in the example we just saw, the regression sum of squares is calculated as thus. Residual sum of squares is this, and this part we had already calculated. And we can thus calculate an F ratio, and comparing this F ratio or F statistic to the F distribution with degrees of freedom 1 and 11, numerator degrees of freedom 1, denominator degrees of freedom 11. Don't forget the order matters. We can calculate the p-value, and in fact the p-value, as you remember, the F distribution is the squared version of the t distribution with degrees of freedom 1, the numerator degrees of freedom 1, And so the p-value you'll be calculating here, and the p-value you would be calculating from this t statistic would be just the same. We can also calculate a statistic that we had learned about earlier, again in ANOVA, R squared. So R squared, as you remember, is the amount of variance we explain with our model. In regression, our model is the regression model. In ANOVA, our model is the grouping, right? So model basically means some explanation of the data. We're trying to explain the dependent variable, the response variable, with some explanatory variable. So the ANOVA, in ANOVA, the grouping is our model. In regression formula, linear regression, our formula is the model. It allows us to make a prediction. So R square is a measure of how much of the total variance is total sum of squares is explained by the model. And here we can use the sum of squares of regression. So this part here, the distance between each predicted value and the mean. Okay, just note the difference between these two formulas. This is the residual, right? The distance between the observed value and the expected value. And this is the distance between the expected value and the mean. So if we have a, perhaps I can show it easier here. So the expected values, for instance, for these 2 points are here, right? Expected value for this one is here. The one is here. And what's the mean of the y values? Probably somewhere here, right? So those differences are basically, if I draw a horizontal line here, those differences would be these ones, okay? And here, and so on, okay? So this is the regression sum of squares, okay, as opposed to residual sum of squares. Residual sum of squares, as you remember, let me change my color. Residual sum of squares is are these values, are based on these values, squared versions of these values, right? Okay, so we are trying to decompose the total variance, which is this is the mean, right? Let me change further our color, magenta perhaps. Okay, if this is our mean, we're trying to decompose the total sum of squares, the distance between each value to the average, to this magenta line, as the distance between the predicted values and the mean, and the distance between the predicted values and the observed values. Okay, so that's what we're doing here. And yeah, so the R squared value is this ratio, and the higher the ratio, of course, the better the fit. If there's no error, if all the observed data exactly fit on the predicted data on the regression line, there's all the data points are on the regression line, then R squared will be 0, right? Whereas if the regression line basically doesn't explain anything, then R squared will be, sorry, I of course just confused. R squared will, in this case, R squared will be 1. residuals will be 0, R squared will be 1. If the regression line basically doesn't explain any variance, R squared will be 0. And here R squared, the amount of variance that we can attribute to the regression model is 0.46. Very good. Okay, so we also have to, of course, think about the assumptions of this parametric test that we're running. We already discussed these briefly, but now we'll be dealing with them in more detail. So we said for each x, we assume that there's a possible distribution of values of y, which are normally distributed with the same variance, and the relationship between each x value and the mean of those population of y values is a linear relationship, as shown here, right? For each x value, we have possible population of y values, and we're basically sampling from these y values. And the means of those y values, they follow the regression line. They're linearly related. X and y are linearly related. These populations of y values, they have the same variance, and they're normally distributed. Okay, so if these assumptions hold, then regression works fine. Yeah, so unlike correlation, we don't have assumptions about x values in regression. X could have it could be uniform, whatever, it wouldn't matter. It could be repeated, that's also fine. Yeah, so now we will be discussing how we can determine if the assumptions fully hold or the data suggests violations of these assumptions. So one common type of violation is, as in the case also in ANOVA and other correlation and other parametric tests, is having distributions that are non-normal, that are skewed, or that include outliers. So outliers in the data among y values, they can significantly influence the regression line estimation. And such outliers can have particularly strong effect if they are, instead of being in the middle, if they're towards the end of the x range. So if we have some extreme values at either ends of the range of observed x values, or the x values we've collected, if we have extreme y values around the edges, then they will have strong influence on the regression line. If we have skewed distributions and outliers due to skewness, we can try transformation, or we can try alternative methods, or we can consider, if we don't trust these extreme values, we can consider removing them. Of course, always reporting what we are removing. Just removing for the sake of removing doesn't help reproducibility in science. So here is an example of some data about some bird phenotype and its presence at different latitudes. And what you see is that across these, some like 15 observations, there is one which is much different from everybody else with respect to how much white it has in its tail, and it also appears at a relatively low value of our x, or of our exponential variable. So if you include this point in the regression curve, you get a relatively flat line, and I guess it was also not, it becomes much less significant. Whereas if you if this point was not included, then the regression becomes much smoother. But of course, just because the regression becomes smoother and more significant doesn't mean that this data is an artifact. It could also well be that there is actually more variation than was sampled in this small data set. So yeah, we have to be careful. This could be an artifact, and if that is so, it might lead to us to conclude that there's no relationship, which could be a false negative. But it could also be that this is a real data point, and if we had collected more data, we would see more of these, and perhaps in reality, there is indeed no relationship. So we need to be careful in interpretation here. But obviously, the presence of this point doesn't make our regression line very reliable. Yeah, outliers can create artificial signals. Like, consider this case of a ball of points where there's no relationship between x and y values, y and x, but just a single point which has outlier status both with respect to x and y. It can lead to a strong positive slope. Yeah, and depending on the value, it might even turn out, I'm not sure how regression, the standard regression analysis would result if we input such data, whether it would be significant or not, I'm not sure, just because it's based on single point. But obviously, we would not be willing to conclude about a correlation and a significant correlation between x and y and a significant slope just based on the single observation. What if you encounter such a situation? What one would do would be go back and check the data to understand why this data point is behaving so differently. And if you cannot figure that out, you would need to say, well, perhaps one needs to collect more data, because there seems to be something weird perhaps going on. Okay. Another type of violation is when the relationship between x and y is not linear. So take this example of data points, number of species observed per area, and it has this kind of nonlinear relationship. In fact, if you added a nonlinear type of regression, smooth with the different type of regression functions that are nonlinear that you could use there, you could find such a relationship, which perhaps doesn't explain the data. It explains data pretty well. Also called local regression, because it divides the data along the x-axis and then performs local small regressions and then joins them. So yeah, this is if you find that the two data sets are not linearly related, then it would be reasonable to explore alternatives. Or you could, of course, also consider transformation of x or y or both of them. We'll see that in a second. Another type of issue is when well, another type of, not another type of issue, I'm sorry. If there is a non-linearity, or if there are skewed distributions on the y, one way to observe that would be to check the residuals against x. Residuals, as you remember, are the difference between the observed and expected values, not the residual squares, but the residuals themselves, which will be distributed around 0. Residuals, the original residuals, will be always distributed around 0. And if there seems to be a relatively uniform distribution with respect to x of the residuals, then we're fine. But if, for instance, as in here, we have both high and low values of residuals at certain values of x, and then less variance in residuals at other values of x, then this is not fine. So here, this obviously suggests there's more variance in y values when x values are small, and there is less variance in y values when x values are large. So the variances of y values are not equal. So this doesn't hold, but it looks as if y values have more variance when x is small. And that's, of course, a violation of the ANOVA assumption, right? Sorry, the regression assumption. So if we plot residuals against x, we can observe such behavior. This is original x and y values. So for instance, income versus age, increase in variance, or gene expression versus age, again, increase in variance. This is brain gene expression, this is income. And if you identify these kind of relationships, then regression analysis isn't appropriate. The linear regression that we learned isn't appropriate, because our power in predicting values here and predicting values here will be different, right? Yeah, so checking residuals against x is definitely something important to perform safe and sound regression analysis. Non-uniform variance of one value against another value where there's a relationship is called heteroskedasticity. Yeah, these are heteroskedastic relationships. We said we could also use transformations to deal with skewed or nonlinear relationships. So for instance, here we see a power function where y is related to x in as a power of a certain power of x, and here we have an exponential function where y is related to x, where x is power of some constant, and we can imagine how if we logged these values, how things would could potentially improve. So if we log here both sides, we will get a relationship that describes the change in values of y as a function of changing values of x, but in both in logged form, and that would become linear. Here we would have x in non-logged form because it was power, and y will be in logged form. So the logged values of y will be changing linearly with the original, with values of x in the original scale. Okay, so such transformations can help converting nonlinear relationships into linear relationships, and it can also help standardize variances. We had briefly learned about how when you log transform data, if there's a relationship between mean and variance, this relationship becomes it can be accounted for, can disappear. And here we see the same example we had seen before. So the relationship between number of species and area, and it seemed to be non-linear. But in fact, if we log transform both variables, we get a more or less linear relationship. It's not perfect, but it's much more linear. So you could potentially perform linear regression on this data. Though, as you see, it would still have, here the residuals would be small, here the residuals would be much larger. So it would still be not super, one wouldn't be super comfortable in doing linear regression here. Another case, so body mass versus testis mass. We had earlier, I think in one of the earlier, in correlation, we had studied this relationship between brain and body mass. Many organs, the mass of many organs is correlated with body mass. But of course, body mass values, they vary among species, even closely related species like mammals, on the order of, many orders of magnitude, so many multiples of 10. So you can have a mouse of just a couple of dozen grams versus an elephant of multiple tons, or at least some tons. And so because the values are so different, when you just plot the original data one against the other, the data distributions are pretty non-linear. But if you log transform both sides, then you can get pretty linear relationships. And again, this is a regression performed on testis mass versus body mass. Body mass being exponentially, testis mass being the response. If you input the original data without transformation, looks like this. Many organisms have small body mass, few organisms have large body mass, and also the residuals here are much smaller, residuals here are much larger. So this is obviously not a nice setting to perform regression analysis. But if you log transform the data, both body mass and testis mass, then perform linear regression, then the distribution of residuals is the original data becomes linear. The regression line fits much nicer, and you can see that improved fit by the nice homogeneous distribution of residuals across different values of x. Okay, and we discussed violations of regression assumptions and how we can deal with them. Now we will be talking about something slightly different, how in regression analysis, how noise in the data will be influencing the regression formula and the significance of the regression formula. So if we have measurement error, introduce just random noise in y or in x, how will these affect the regression analysis? This is our question. And you can try to imagine what can be, what could go on. So in general, of course, the higher the noise, the lower the power. So the significance of the relationship will become weaker. It will be more difficult to say there is a real relationship, non-random relationship. But on top of that, depending on whether error is introduced in y or in x, the slope will be changing differently. So if the error is only in y, if there's additional error only on y values, then there will be more variance. So the MS residuals, residual mean squares will increase, right? Data will come from a nicer, tighter fit to a looser fit. But the slope doesn't necessarily, it doesn't change. But if we introduce noise on the x variable, if x were noisy, then that will also make the slope approach zero. And why is that? I mean, easy to imagine. You could, let me show here. So adding two data points, for instance, here and here, this won't affect the slope. But adding two data points here and here on the, if we add noise in the x, so a point that was supposed to be here, having two observations here and here, this will make the slope much weaker. The variance, as you remember, the slope formula. What was the slope formula? I have to go back. Yeah. The slope is the ratio between the sum of products and the sum of squares of x. And as the sum of squares of x increases, the slope will also decrease. And so we will, give me a second. Let me go back to a slide here. Yeah. If we have noise on the x, so noise here, both sides, it will make the slope weaker and weaker. So yeah, just to repeat that, noise in y, it affects the significance. It weakens the weakens power to reject b being zero. Actually, I should have put beta here, but it doesn't affect the slope. But noise in x, it reduces power again, but it also reduces the estimate of the slope. It pushes it towards zero. Okay, I hope that is clear. And now we'll be talking about nonlinear and logistic regression towards the end of this chapter. So if we have such data, this is in fact some kind of Michaelis-Menten type relationship, concentration of some factor and the responding growth rate. And we have data points. As you see, there does seem to be some relationship, but here we've people have added such a regression, a nonlinear regression that manages to pass through each data point. There are no residuals, as you see, because the line actually passes through all the points. But it's a very complicated model to construct such a model, the model probably has at least as many parameters as the data points. And this is called overfitting. So, for instance, based on this model, we would be expecting to observe, if the model would be true, it would be predicting that the growth rate at iron concentration 1.5 should be somewhere here, and the growth rate at iron concentration 1 should be here, and so on. But in fact, do we really believe this curve or this curve? Do we really have enough data points, enough evidence to rely on this shape, to trust the shape of this regression curve? No. Obviously, there's too little data, and the model is too complicated for too little data, and that's called overfitting. Okay, and that's common, problem in machine learning, having too complicated models given too limited data. So the predictions with such models will also be not very helpful. In general, the simpler the model, the fewer parameters we use to describe the data, the better. And in fact, one can explore. It won't be something we will study further, but as a general idea, if you have such data, you could explore different mathematical models that could potentially explain such relationship that people have come up with. And for instance, in this case, the same data, here is the same data, can be explained by such a curve with just two parameters. Again, as you see, it's not a linear relationship. It's a bit more complicated, but it has just two coefficients, just two parameters, and it provides a pretty nice fit to the data. And the predictions based on this model, on this nonlinear regression model, would be pretty reliable. We could say the residuals are very small again, and it's simple and reliable. So if you have such data, it would make sense to try to see what kind of non-linear simple models people might have come up with to explain your data. You could also have such curves, something that goes up and down in many instances. Let's say the energy metabolism over life, it first goes up and then down. Many functions have this type of quadratic relationship, and you could then use quadratic or polynomial regression. You could also add more terms, of course. Again, here we're explaining the data with just three coefficients, right? Model with just three parameters. It's a bit more complicated than linear, but it's good enough. It could be good enough. Okay. And there are also nonlinear regression algorithms that provide more complicated, that are based on more complicated functions. There is this the danger of overfitting, as in here, but sometimes the relationship between the exponential and response variables are indeed complicated, and there is enough data to rely on such functions. Lewis regression splines, kernel something. These are different versions of such nonlinear regression functions. And here we have such an example of, I think it was seals, of which the bodies were measured across their lifetime, many individuals, as you see, and this is not the super nice example because the data, there are some gaps in the data. And in some seasons they cannot measure apparently, but in some other seasons they measure the lengths of the females, and apparently there is some flexibility of the body. It suggests that, okay, they continue to grow for, what's that, some multiple years, but the growth is not monotonous, and in some seasons they grow larger and then they grow smaller depending on how much time they spend in the sea or on land, etc. And yeah, so this type of relationship, this ups and downs, it can only be observed by such a nonlinear regression function. I think they were using Loess here. I don't remember exactly. And of course, you might rightly suspect whether these peaks are significant or not, but there is quite a lot of data points, so most likely they are significant. Yeah, so these nonlinear regression functions, they have different, they're usually flexible in that they can allow different amounts of smoothing. Smoothing is how flexible you allow the function to be. So this was obviously pretty flexible. This was extremely flexible, as you see, and this was this is a much smoother curve, not as flexible. But then, yeah, you can many functions have a parameter that you can play with the smoothing, and here is an example from R, the speed and some distance with some other variable, and this is the original data with degrees of freedom 2.6. Degrees of freedom is a measure of how much smoothing you allow. You get some kind of slightly curved curve, whereas if you also allowed a higher degrees of freedom, that would mean higher flexibility. So then that would create this regression curve, which is much more much more flexible, as you see. So it tries to follow the data points more closely, but it could be the higher the degrees of freedom you allow, the higher the risk of overfitting. So it's not really clear if the red curve, at least to me, looking at this, whether the red curve is really better than the blue curve as a predicting model. Okay, and last type of regression we will learn is logistic regression. Multiple regression we'll learn later. Yeah, so logistic regression, it's we had mentioned this in the first part of the lecture. It's a type of regression where the response is binary. It's 1 or 0. So mortality, infection, any other type of binary biological variable can be analyzed as a function of quantitative variables. So for instance, yeah, in the example here, you have anthrax dose, how much anthrax some poor rhesus monkeys have been given, and the response is whether they died or not. And of course, a monkey can only die or survive. The anthrax dose is a quantitative variable. The experimental variable is quantitative. The response is binary. And yeah, in many biological problems, you have such kind of a setting, the response being binary. And in that case, in these kind of cases, how can we treat the data? Just using the ones and zeros, the response ones and zeros in a classical linear regression framework, it doesn't help. Obviously, many of the assumptions would be violated. So what you do is you transform the response using a logarithmic transformation. But it's not just if you calculate log of 0 anyway, as you know, is it doesn't work. So what you do is you calculate the you use the logarithm of the ratio between y and 1 minus y. Y is the response. So this becomes something like a odds of success case. So the success probability and the failure probability. You can think of it like that. And the log of that odds value, log of that ratio. And this now becomes your response. You try to model this response, the relative probability of success, as a function of your quantitative variable. Okay, a linear function of your quantitative variable. And how you exactly do that, how you do the calculation, we won't learn, but it's good that you learn the general principle, the logic, because logistic regression is used in many different settings. It's you could also see this as a classification problem, like many types of problems machine learning deals with. So you have different types of images, let's say, and you're trying to classify them into male or female, dead or alive, X way or Y way, two binary types. And logistic regression is a simple approach to do such classification. Yeah, and the response, again, as we said, is a relative. You could see it as a relative odds of it's odds of log odds of success. And once you define this relationship, you can also rewrite it as follows: y being a function of x, where involving this exponential term. Yeah, people have also been using other types of models. You could also have different models here, of course, but this is a very common approach. And then, of course, comes the problem of how to best find the function to describe the relationship between x and y, or this transformed y, and that is done using maximum likelihood, which we will learn next week. Very briefly, you scan over different sets of values that would minimize the residuals. So instead, in least squares, we had a simple method to calculate to find the regression line that minimizes the residuals. If you don't have such a simple formula, you can also try different values and see with what kind of alpha and beta values would you have minimal residuals. And with computers, this is not so difficult in many instances. Okay, yeah, this is basically an example where you have different x values and the experimental variable, the response variable is 1 and 0, right? So here for each x, for when X was 28, the response happened as failure 4 times and success 1 time. When the exponential variable was 33, the response happened as failure 1 time and success 14 times. And now you can convert these values into odds of success and log odds. That's this value, right? The y you observe the proportion of successes divided by 1 minus the proportion of successes. And then you try to come up with a regression curve that is not a linear regression curve, but relationship that where the alpha and beta are chosen such that the residuals are smallest. And that in this case, for instance, this formula would is estimated as again, I think using maximum likelihood as the log of odds of mortality as a function of dose. The higher the dose, the log of odds of mortality, here success being mortality, ironically. The higher the dose, the higher the probability of mortality, and this is the relationship between the two. Okay, and our last topic here after logistic regression is this, we come back to the history of regression. In fact, you might have naturally wondered why regression analysis is called regression analysis. Regression is going back, right? Its meaning is going back. We didn't encounter any phenomena until now in this analysis which was related to going back or retreating. So what is what's going on? What does regression analysis have to do with regression? Well, it turns out that the people who first developed this regression analysis, in fact, it was Galton, a eugenicist from the end of 19th century, was also a relative of Darwin, and he was trying to find, understand how different phenotypes are related between parents and their children, and he was collecting data and studying the relationship between these two quantitative variables. And within this effort, he developed some of the basic concepts of regression analysis. And what he also noticed was that the children of very tall parents, they tend to be tall, but not as tall as you would expect from their parents' heights. Okay, so what you would expect from the parents' heights would be something here, but their children would tend to be somewhat less tall. And just the opposite for children of parents who were short, who were extremely short. Their children were not as short as you would expect from the parents. So mid parents means the average of the two parents' height. So this behavior, what he defined as regression towards the average, so extreme values in the next generation not appearing. And this is in fact this behavior of data, this behavior about extreme points is observed in many instances when you have a random variable and an individual is measured twice for the variable. And here you could think of families as the height of the parents and the height of the children as two independent measurements from the same family. And if you look at the most extreme cases of the first measurement, okay, then the second measurement, in the second measurement, those are not necessarily as extreme as in the first. They also, of course, if there's some repeatability in the data, you remember this concept of repeatability from ANOVA, from random effects of ANOVA. If there's some repeatability, the tallest observations in the first measurement will also tend to be tall in the second measurement, but not necessarily as tall. And that's because this extremeness is usually partly repeatable and partly random. And that randomness is usually not repeated. And so, yeah, when you compare the two measurements on the same individuals, on the same units, the most extreme values for the first measurement, the lowest ones or the highest ones, for the second measurement, they will tend to be, they will tend to have values which are smaller. And that's called the regression towards the mean, towards the average. Okay, and that's again because the most extreme values are extreme both because of some repeatable, reproducible nature of theirs, but also because of luck. And in the second measurement, that luck is usually not repeated. You can be lucky once, but not twice. Yeah, so that's what is being described here. So please solve the questions at the back of the book, of the chapter. And this is our last main chapter where you'll be needing to solve exercises. And the next week, it will be a long series of lectures on four different chapters. And it will be important for you to learn as students of biology, molecular biology, those different tools as well to get familiar with what's possible in statistics and computational biology and bioinformatics. But yeah, this marks the end of the part of the course where we will be solving problems. Okay, so see you on Monday. Take care.